One way to approach this problem is to try and compute the expectation directly from the probability distribution of the wait times. But in order to find the probability distribution of the wait times, first we need to find the distribution of the first meal, of the time of the first meal, and then we need to find the distribution of the time of the second meal, and then we need to find the distribution of the wait time, that is to say the difference between the time of the first meal and the second meal. So we actually need the time of the second meal given the time of the first meal. Okay, and then once we have the probability distribution of the wait time, we can compute the expectation. But this seems like a lot of work. Finding the distribution of the time of the first meal is already kind of tricky. And then finding the distribution of the second meal given the first meal is at least as tricky. And then finding the difference between these two distributions is probably even trickier. And then computing the expectation may or may not be difficult depending on the nature of the distribution we found in number 3. So let's look at this problem a little more closely. The 3 meals are distributed uniformly at random throughout the day. And then let's denote the wait times between the meals as x1, x2, and x3. Since there are 24 hours in a day, we have that x1 plus x2 plus x3 is equal to 24. But we also have symmetry in this problem. That is to say the distribution of x1, x2, and x3 should be identical because in some sense there's nothing special about what's considered the first meal, the second meal, and the third meal. So thus we can say that the expectation of x1 is equal to the expectation of x2 is equal to the expectation of x3. So taking expectations of both sides of this equation, we have that the expectation of x1 plus expectation of x2 plus expectation of x3 is equal to 24. And since all 3 of these are equal, we have that the expectation of x1 is equal to the expectation of x2 is equal to the expectation of x3, which is equal to 8. In the previous part, we determined that the expected wait time between meals is 8 hours. So at first glance, we might guess that the expected value of x is 4 hours, or 8/2. The reasoning behind this is that if your friend calls at a random time in an 8-hour block, the expected amount of time between her call and the next meal is going to be 4 hours. But this is slightly misleading, because the amount of time between meals is not exactly 8 hours. The amount of time can be either shorter than 8 hours or longer than 8 hours. And it's not clear that the effects of these two cases cancel out. So we should work this out more carefully. So we can kind of treat the call as a 4th meal. That is to say, the events of figuring out what times your meals are at and what time your friend calls are exactly the same. So using the argument we had from the previous part, if we have 4 events now, and we call these events x1, or the wait times between these events x1, x2, x3, and x4, we have that the expectation of x1 is equal to the expectation of x2, which is equal to the expectation of x3, which is equal to the expectation of x4 by symmetry. And similarly, the sum of the xi's from I between 1 and 4 is 24. So therefore the expectation of xi is going to be 6. In particular, the amount of wait time between her phone call and your next meal is expected to be 6.